Let's now develop our stability criterion for the closed loop. So we had said earlier that the closed loop was where the response was referred to the set point, and we had found that it had the relationship with the open loop that looked like this. And we had also said even earlier than that when we have an equation of this form, that the poles of the function is where we have the eigenvalues of our response. And that's where we want our eigenvalues to be, to have negative real parts. So the poles are the values where the denominator goes to 0. So we are concerned about the solutions to this, the denominator going to 0. So those will give us, so the S values that cause the denominator to go to 0, those S values are the eigenvalues, and we want those S values to have negative real parts. So that's the criterion now. 1 plus G open loop equals 0. The S values that correspond to this, we want to check whether those have negative real parts. And so we can say that the zeros of this function are the poles of G closed loop. So the poles of G closed loop are where we have the zeros of 1 plus G open loop. So we'd like to know about the zeros of this function, and we want to know that those zeros have negative real parts. Now, we've just looked at the principle of the argument. It says if we have a closed contour, then the number of encirclements of our function equals z minus p. So we'd like to use this. And that seems a little bit complicated because that's a closed contour. What we actually want to know is where we have negative real parts, or we want to know if we can ever have a 0. Remember, 0 here is a pole of that. So we want to know if we have any zeros of this function which have positive real parts. And for that, we need a contour. We need to travel around a contour and see if there are any zeros in that contour. And our contour needs to contain all the possibilities of positive real parts. And we can do that. We can create such a contour if we imagine a disk like this. So a semicircle where we start from 0 and we go off to infinity along this axis. So this is, of course, the function s equals I omega. So let's let omega be the distance we've traveled along this axis. So if we let s equals I omega and we let omega go off to infinity, and then let's say we pick some point where omega is tending to infinity. Then if we travel as our next path, if we travel around this part of the disk, so this curved part, so this is now subtending the entire right-hand plane. Remember, omega equals infinity. So this is an infinite semi-disk. So we are traveling around the entire right-hand plane. And so that's going to include all possible positive values for the real part of S. So imagine we are going around the entire right-hand plane, then we end up down here on negative infinity. And then if we travel straight back up to meet the origin again, then we have constructed a contour that goes around the entire right-hand plane. In other words, it's the contour that will contain all possible positive real parts, right? Remember, this half of the plane is where we have positive real parts. So that would be the contour for us. So we could then say, well, if we can travel around that whole contour, and so we adopt all the S values around that right-hand plane, then those S values, if we stick them into G closed loop, and if we see G closed loop going through some number of encirclements, so as we did all that, if we observe G and if it goes around the origin a certain number of times, then that will be the number of zeros minus the number of poles of that function. So that's one thing we can do. And we can say, but then, well, what if we have a certain number of poles that's not 0? Then we still won't know if we have we still won't know the number of zeros that we have in the right-hand plane. Well, we can say still that if our process is inherently stable, right, an inherently stable process will not have any poles in the right-hand plane. So if we have no poles in the right-hand plane, then our P equals 0. And then we can say the number of encirclements will equal the number of zeros. And so as we move around this entire right-hand plane in this way, remember, going from the origin, going off to infinity along this axis, then going around this semicircle, this infinite semicircle. And so we cover all possible real parts being positive. And then we come back along this line. Then we have completed a contour. So as we do all that, if we observe that G closed loop goes around the origin even once, then that means we do have a 0 in the right-hand plane of this function. And so then we would say it's not stable. So we are concerned about doing that and seeing that n is more than 0. So we would like to test that. And so we have established a criterion now, right? We've broken down our contour into these 3 pieces. And so as we travel around there, that's what we're going to look for. We'll look for encirclement, and that will tell us the number of zeros. So this is the basis for the stability check. And we could say, well, the function that we are actually concerned about is this one. We want to know about the zeros of this function. So I may have said once or twice that we are observing G closed loop, but it's actually not the whole of G closed loop we have to look at. It's actually this denominator. We are concerned about having zeros of this denominator in the right-hand plane. So that's what we are looking for. We would plot 1 plus G open loop, and as we travel around here in the S-plane, we would look in the 1 plus G open loop plane to see if we ever encircle the origin. So we could say, well, we can do it that way. We can plot that function. We could say, well, instead of working with 1 plus G open loop, we could instead recognize that 1 plus G open loop encircling 0, 0, that's equivalent of just looking at G open loop and subtracting off that 1, and then looking for encirclement of -1, 0. So once more, we can find the point -1, 0, which will be somewhere here. And we can say, as we let S go through all these values, and then we observe G open loop. And if G open loop ever encircles -1, 0, then that's the same as saying 1 plus G open loop has encircled the origin, and that means that we do have a 0 in the right-hand plane. So that's our criterion. And we can then think about traveling around this right-hand plane, and let's see if we can't simplify that a little further. So we have said S equals I omega, so that's traveling along that axis. So we'll keep that. Then this next piece, we have to travel around this semicircle. So we've represented it this way. We've said the magnitude is infinity, and the angle is going from plus 90 degrees. We can see here, if we are taking the angle from this axis to this to this line, then we can see we are on a plus 90 degrees. So we start there on plus 90 degrees. And as we travel around here, we are decreasing the angle. So from plus 90, plus 80, plus 70 to 0. And then we are going through negative angles until we reach minus 90 degrees. So that's that path. We are at infinity. So we are an infinite distance away, and our angle is plus 90 degrees. And then it travels around until we reach minus 90 degrees. So that's that part of the path. And if we think about S values like that, and if we think about our G open loop function, remember G open loop looks like this. By the end of the day, we can decompose it into a form where we are multiplying S minus Z up to M of them in the numerator, and S minus P up to N of those in the denominator. And we've said this process is inherently stable, right? We said if G open loop is inherently stable, then P equals 0. So that's how we simplified it to N equals Z. We said there are no poles in the right-hand plane. And so if that's true, then the process is inherently stable. Then that means M is less than N. So for instance, here we'll have, perhaps this could be S cubed. Then in the denominator, we'd have to have at least S to the power 4. So in a case like that, where your denominator has a greater order than your numerator, then when S goes to infinity, that means this whole term on the right-hand side, that must go to a 0. So our G open loop, when S has a magnitude of infinity, G open loop is going to have a magnitude of 0. So that means we can never encircle -1, 0 when we are traveling around here. So when S values are sitting on this semicircle, then G open loop will have a magnitude of 0. And so G open loop can never encircle -1, 0 anywhere when S has values here. So we can say, then we don't even need to check this part of the contour. We can never encircle when S is moving around here. So we can just ignore this part of our contour. Then when we also look at this part of the contour where we are at -infinity and coming back to 0, we recognize that S equals -I omega along that path. And that's just the complex conjugate of the first part. So in the first part, we went S equals I omega like so. And this is just the complex conjugate. So what we'll get for G along this part of the contour is nothing but the complex conjugate of what we got for this part of the contour. So in other words, all encirclements of -1, 0 will already have been observed along this path. So it's pointless even looking at this part of the contour. So that reduces the places we need to check. We only need to check S equals +I omega then. So that nicely summarizes everything for us. It says all we need to do is check along S equals I omega. And if G open loop ever encircles -1, 0 while we're doing that, then it means we violated our stability criterion and the process is not stable. So that establishes a nice criterion for us. And it's nice and simple. All we need to do is travel along S equals I omega, and then we observe G open loop while we're doing that. And if G open loop ever encircles -1, 0 while we're traveling there, then we've violated our stability criterion. And all violations that we see there will be everything possible. We can never violate it moving along there. And we will not see new violations if we travel along this one. So that's the only one we need to check. So from all that logic, that is the simple criterion that emerges.